Solving quadratics by finding square roots. A number r is a square root of a number s if r squared equals s. So when you're finding square roots, you're thinking to yourself, what number did I multiply by itself to get the number under the radical symbol? Some vocabulary to learn. So if we have the square root of 14, it's called a radical. The radical sign is this symbol, and the radicand is the number that sits under the radical sign. Key concept. Properties of square roots. As long as a is greater than 0 and b is greater than 0, the product property applies. The square root of a times b is equal to the square root of a times the square root of b. And we use this property a lot when simplifying radicals. For example, if we had the square root of 18, we could think of that as the square root of 9 times 2, and use the product property to break it down into the square root of 9 times the square root of 2. Then the square root of 9 is just 3. Square root of 2 doesn't square root evenly, so we leave it. And we have our simplified radical form, 3 square roots of 2. There is a very similar quotient property. So if we have the square root of a divided by b, that's equivalent to the square root of a divided by the square root of b. For example, if we had the square root of 2 divided by 25, we could split it up as the square root of 2 divided by the square root of 25. The square root of 2 is not a nice whole value, so we'll leave it. The square root of 25, though, is a nice whole value of 5. So we have the square root of 2 divided by 5 in our simplified form. In Unit 0, you reviewed how to simplify radicals. Here are some additional examples and reminders of those. If you have the square root of 80, you want to find the largest perfect square that divides into 80 so that you can break it down into factors. So with 80, the largest perfect square that divides evenly into it is 16. So we'll break it down into 16 times 5. We can use that product property to break that into the square root of 16 times the square root of 5. And then the square root of 16 is 4. Square root of 5 is not a nice whole value, so we leave it. And there's our simplified radical form. We can also use the product property in reverse. If you've got the square root of 6 times the square root of 21, well, 6 is 3 times 2, 21 is 3 times 7, so we could combine these into a single radical and have 3 times 2 times 3 times 7. The important thing is that we now have 3 times 3. So we have a 9 under the radical. The 2 is prime and the 7 is prime, so we're not going to be able to break those down. We can go ahead and multiply them to get 14. So then I can think of it as the square root of 9 times the square root of 14. The square root of 9 is 3. The square root of 14 doesn't come out evenly, so we leave it. And there's our simplified radical form. You could have simply multiplied 6 times 21 and gotten 126, but then you'd have to break that down into 9 times 14 and continue. So sometimes it's easier to do it in the method I showed, where we break it down into factors first, so that we have smaller numbers we're looking at and we can easily see what perfect square factor divides into it. Question 3 is already split up with the quotient property. The square root of 7, well, 7 is prime and it doesn't square root evenly, so it's going to stay the same. But in the denominator, we can square root the 16 and get 4. So we can simplify it down to the square root of 7 divided by 4. We also have to rationalize the denominator of our radicals. The denominator of any fraction must always be a whole value. So we cannot leave a square root in the denominator at any time. This is a skill that we will expect you to perform throughout the course anytime you're dealing with radicals. So we're going to use the quotient rule on number 4 and split it into the square root of 5 over the square root of 2. And the problem is that square root of 2 in the denominator. To rationalize it, to turn it into a nice whole value, I'm going to multiply top and bottom of the fraction by the square root of 2. The product rule allows me to turn that into a single square root in the top and the bottom, so that I now have the square root of 10 over the square root of 4. Well, 10 does not square root evenly, and it doesn't have any perfect squares inside of it, so we'll leave it square root of 10. 4 square roots evenly, though, so that I have the square root of 10 divided by 2, and that is now an acceptable answer. The denominator is a nice whole value. It's been rationalized. We'll do the same thing on number 5. We'll use the quotient rule to split it up into the square root of 2 divided by the square root of 15. Now we're going to multiply top and bottom by the square root of 15, and we do the top and the bottom because that means we're multiplying by a value of 1. So we're not changing the value of the fraction we have, just the format in which it's written. So again, I can combine that via the product rule into a single square root, so that I have the square root of 30 over the square root of 225. Well, 30 doesn't square root evenly. It also doesn't have any perfect square factors. It's 5 times 6. 6 is 2 times 3, but those are all primes, so I can't break it down. And the denominator of the square root of 225 is 15. You can also identify that from the beginning, that if you do a square root of 15 times the square root of 15, you're squaring a square root, which are inverse operations, so it's just going to cancel the square root and leave you with 15. In this next section, we'll still be rationalizing the denominator, but this time the denominator contains a binomial, 2 terms being added or subtracted. This may be brand new to you. In order to rationalize the denominator, we use what's called the conjugate. The conjugate is the same binomial, only the opposite sign. So we're going to multiply the top and bottom of this fraction by 7 minus the square root of 2. And the reason we do this is when you multiply conjugates, the center term drops out. Think about difference of squares when factoring. When you take something like x plus 9 times x minus 9 and you multiply, you end up with x squared minus 81. The center x term is 0, so it completely drops out. So if I take 7 plus the square root of 2 and multiply by 7 minus the square root of 2, what will happen is my radicals will be completely eliminated, and I'll have a nice rational whole value in the denominator. So let's see that. In the top, I have to use the distributive property since I have a monomial times a binomial. So 3 times 7 is 21. When it comes to the 3 times the square root of 2, I can't actually multiply them because the 3 is not under the square root and the 2 is. So I just sort of shove them next to each other to show implied multiplication, that it's 3 times the square root of 2. In the denominator, you're going to use FOIL or a generic rectangle. So 7 times 7 gives me 49. 7 times negative square root of 2 is negative 7 square root of 2. Positive 7 times the square root of 2. And then negative square root of 2 times positive square root of 2 will give me negative square root of 4. So in the top, I don't have anything I can simplify, so I leave it the way it is. But in the bottom, negative 7 square root of 2 plus 7 square root of 2 is 0, so the center term drops out. And I have 49 minus, well, the square root of 4 is really just 2. So my final rationalized fraction, 21 minus 3 square root of 2 over 47. So there's my fraction with a rational denominator. Same idea on the next one. I just need to move things around quick and gather a little space. Okay. So, to rationalize the denominator on number 7, again, I'm going to multiply by the conjugate. So I'm just going to flip the middle sign for my binomial in the denominator, and so I'm going to multiply by 5 plus the square root of 2 over 5 plus the square root of 2. Again, distributive property in the top, since it's a monomial times a binomial, so we get 20 plus 4 square roots of 2. In the denominator, FOIL or generic rectangle, so I get 25 plus 5 square roots of 2 minus 5 square roots of 2 minus the square root of 4 when I do square root of 2 times square root of 2. So in the top, nothing I can simplify. In the bottom, I have 25 plus 5 square root of 2 minus 5 square root of 2 is 0, so the center drops out, and the square root of 4 is really 2. So we'll get 20 plus 4 square roots of 2 over 23. And now the denominator is rationalized. It's a nice whole value. One great application of square roots is to solve quadratics. For example, if s is greater than 0, then the equation x squared equals s has two real number solutions. X equals the positive square root of s, and x equals the negative square root of s. These solutions are often written in condensed form as x equals plus or minus the square root of s. We can only use square roots to solve quadratic equations when they have a quadratic term, so something squared, and a constant term, so regular numbers. If they have a linear term with an x, they're not set up to be solved with square roots. So that's the first important thing, is that you have to learn to identify when you can use square roots and when you cannot use square roots. So in example 8, we see we've got a quadratic term, squared, and constant terms. There's not any terms where we have like 2x. If we have an x to the first power, that's a problem, and we need a different solution method than square roots. Because this one doesn't have that, and it just has the quadratic and the constant terms, we can go ahead and solve it. So we start to solve it as if it were a linear equation. We're trying to isolate the x squared, so I take away 5 from both sides. Then I divide by 3. And I have that x squared equals 12. Remember that the opposite of squaring is to square root. So we square root both sides. When solving an equation and you take a square root, you have to remember plus or minus every single time. So we have x equals plus or minus the square root of 12, but I can't leave it as 12 because there's a perfect square inside of that. It's 4 times 3. So I break it down into the square root of 4 times the square root of 3. I square root the 4, and so my answer is x equals plus or minus 2 square roots of 3. Same exact steps on number 9. Add the 15 to both sides. So 2x squared equals 80. Divide by 2. So x squared equals 40. Square root to undo the squaring. You see that x equals plus or minus the square root of 40. Again, I can't leave it square root of 40 because there's a 4 inside of that. So I break it down into plus or minus the square root of 4 times square root of 10. I get plus or minus 2 square roots of 10. In problem 10, so it's a little bit of a different setup, but it still works because I still have a quadratic term, something squared, and then the others are just constant terms. So first thing I want to do is get rid of this 1/3. Normally we would divide away the coefficient, but because it's a fraction, we don't divide by fractions, we multiply by the reciprocal. And this is my only option. I don't want to multiply out the binomial. I don't want to take x minus 4 times x minus 4. Then I'm just expanding things and causing myself to do a lot more algebra than I need to. I also cannot distribute the 1/3 inside because the exponent has to come first. My goal is to undo all of this and work toward the x. So I have to start by multiplying both sides by 3. So we have x minus 4 squared equals 33. Then we undo the squaring. So we square root both sides, and we get x minus 4 equals plus or minus the square root of 33. I think about whether I can simplify the square root of 33, but 33 is 3 times 11, which is prime. So I know I can't simplify that. I just finish solving by adding the 4 to the other side. And we always put it in the front so that it's clear it's not part of the square root. It is 4 plus or minus the square root of 33. And that's your answer. Okay, so here's another example very much like the last one, only multiple choice. Give it a try. Do the same exact steps. So we'll clear the 1/5 by multiplying by 5. And we'll get z plus 3 quantity squared equals 35. Then we need to undo the squaring, so we take the square root of both sides. And we see that z plus 3 equals plus or minus the square root of 35. 35 is 5 times 7, so I can't simplify it down at all. All I can do is subtract the 3 to the other side. And again, we put it in the front so it's clear it's not part of the square root. So our solution is negative 3 plus or minus the square root of 35. So if we wrote them out separately, it'd be negative 3 plus the square root of 35, and negative 3 minus the square root of 35. So that is letter C. Let's look at another application problem. So when an object is dropped, its height in feet above ground after t seconds can be modeled by this function. The height is equal to negative 16 t squared plus h sub 0, where h sub 0 is the object's initial height in feet. The graph of h equals negative 16 t squared plus 200 representing the height of an object dropped from an initial height of 200 feet is shown below. The model assumes that the force of air resistance on the object is negligible. Also, this model works only on Earth. Gravity would change if we left the planet. For planets with stronger or weaker gravity, different models are used. For more information, you can check out exercise 39 in your textbook. So that's the setup. Let's take a look at what the question is. Okay, so for a science competition, students must design a container that prevents an egg from breaking when dropped from a height of 50 feet. Move this a little so I can move this over here. How long does the container take to hit the ground? Well, so they're telling us that the initial height is 50 feet, so we fill that in for h sub 0 in our formula. If they want to know how long until it hits the ground, that means that our height would be 0 if we're on the ground. So here's the equation we need to solve, and it's set up that we can use square roots to solve it, since it has a quadratic term and constant terms. So I want to isolate my variable and move my constant to the other side. So we have negative 50 equals negative 16 t squared. I'm going to divide by negative 16. So a negative divided by a negative is a positive. 50 divided by 16 does not come out evenly, but we can at least reduce it by 2 and say 25/8. So then we need to square root to undo the squaring. So t will equal plus or minus the square root of 25/8. So I'm going to use my quotient property to split that up into the square root of 25 over the square root of 8. So I get plus or minus 5. I have to break down the 8 into 4 times 2. So that we can do the square root of 4 times the square root of 2 and get plus or minus 5 over 2 square roots of 2. We'd have to rationalize that denominator and multiply by the square root of 2. So if we bring it over here, we have t equals plus or minus 5 square roots of 2 over 2 times the square root of 4. So plus or minus 5 square roots of 2 over 2 times 2. So plus or minus 5 square roots of 2 over 4 would be the exact fractional answer. But we have to think about the problem. A negative time wouldn't make sense. That would be like before we dropped it. So I guess when we start on the ground and take it up to the 50 feet, we need to know how long from when we drop it, so we want the positive time. And so we probably want to turn this into a decimal approximation. So if you type 5 times the square root of 2 divided by 4 into your calculator, make sure you end the square root and make sure your calculator knows that 5 times the square root of 2 is the whole numerator, and then you're dividing by 4. You should get approximately 1.8 seconds until the egg would hit the ground. So I just wanted to add one more note about when you can use square roots to solve and when you can't. So this is what I'm talking about. This is a quadratic term because it's squared, it's to the second power. This is a linear term because it's x to the first power. If we graph it, it would be, something, when you graph something and x to the first power, it's a line. It's linear. This is our constant term because it's just a number. If you have a linear term in your equation, it is not set up to use square roots for. We will talk in future lessons about how we could force it to be set up in order to use square roots to solve it, but in its current form, it would not be ready to do that. You would have to consider factoring, quadratic formula, or the process we'll talk about, completing the square, to force it to be ready for square roots. So, a couple quick examples. If we have 2x squared plus 1 equals 5, check. We can solve that with square roots. Just isolate the squared term and then square root. We can also do things like this, where you've got something squared. Again, isolate the squared term, square root, and solve. But do not start attempting to use square roots to solve every quadratic you see, because it will not work if you have a quadratic that looks something like this. It is not ready to be solved with square roots. You would have to do a bunch of algebra in order to prepare it. And it's because of this term right here. You would want to think factoring, quadratic formula, which we'll talk about in future lessons, or the process of completing the square. And again, we will talk about that in future lessons. So study and make sure you understand when we can use square roots, and if you can use them, put it to work. It's an efficient solution method, and when you absolutely cannot and need to consider a different option.